even by simple eye inspection you can distinguish between the, let us say, the Poisson and the other two processes. The Poisson has much more clumps and to compensate for it more white spaces, and Ginevra and Gaussian zeros they are locally repulsive processes. So, as a result they exhibit a more orderly behavior. But even here, just before jumping ahead, I would like to point out that if you just compare the Ginevra ensemble and the Gaussian zeros between themselves, it is not so easy to tell them apart. So, for example, if you consider the whole probabilities, which is probability that no points in a disk with center of 0 and radius r. So, one popular or common way to let us say compare point processes is to study the asymptotics of whole probabilities, and it is known that in both the Ginevra and the Gaussian zero processes, the whole probabilities exhibit the same asymptotic order. So, this converges to a constant. Of course, this constant is different for the Ginevra and the Gaussian zeros, but the asymptotic order is sorry, it is a bad place, right? Yes. So, the asymptotic order is the same. So, in some sense this kind of explains the similarity, but both these processes are ergodic point processes. So, they are mutually singular. In subsequently in the talk, hopefully we will see some statistics by way of which we can distinguish between the two. So, I will come to it in a moment, the complete definition. So, first of all, let me define the Ginevra ensemble. So, the Ginevra ensemble is you can obtain it as a limit of finite ensembles. The finite ensembles are for finite n, you consider the eigenvalues of IID Gaussian matrix, and there is no normalization by square root n. And you consider the eigenvalues of this matrix, and you take limits as point processes, weak limits. So, the limit exists, it is a infinite point process on the plane, and it is translation invariant and in fact ergodic, although there is no invariance in the finite ensembles. For the Gaussian zeros, there are more than one way of looking at the Gaussian zero ensemble. In analogy with the Ginevra ensemble, we can obtain it as a limit of finite ensembles. This time, instead of matrices, eigenvalues of matrices, we have zeros of random polynomials. So, the polynomials are these so called well polynomials, which are here. So, the coefficients are IID Gaussians with this particular scaling square root n factorial, and you compute the zeros and you take limits as n goes to infinity, weak limits. And in fact, this coincides with so you can interchange the order of limits. So, you can first take the limit of the polynomials as an entire function and compute the zeros, and the distribution of those zeros is equal to what you get as the limit of the zeros of random polynomials. So, this limiting point process is also translation invariant and ergodic, although there is no invariance in the finite ensemble. And in fact, so about this particular scaling, it is known that essentially this is the unique way to scale square root n factorial, so that the limiting zeros are translation invariant. So, this is essentially a result due to Misha-Sodin. So, this infinite power series with this particular scaling is unique up to a deterministic multiplier if you want to have Gaussian coefficients and invariant set of zeros. So, these are the two main models we are going to talk about. So, are there any questions? up to deterministic multiplier. So, if you take an entire function and if you just multiply it by a deterministic function, it will be, I mean, it will.
So you're saying if I make any other choice, if I multiply coefficient, then it will not change the problem. It will be the same.
Yeah, I mean, okay. So, if you want to have Gaussian coefficients with some scaling, and you want an invariant set of zeros, then that random entire function is going to be this multiplied by some deterministic entire function.
If I choose a coefficient aj in front of the cj,
yes,
no matter how I choose, I will end up to be the same process.
if you have an invariant set of zeros. Okay, so
This coefficient it's a function, it's a deterministic function.
yeah, it's a function, but they have the same zeros. Okay, so the kind of question we are going to ask about these processes is as follows. So, suppose you have a domain in the complex plane, bounded domain. I will come to the exact technical conditions in a moment. So, and if you know the points outside this domain, what information does it give you about the points inside? In particular, the kind of information we are looking for is whether the outside point configuration determines something, it imposes some hard constraints or rigid constraints about the inside. For example, does it determine some statistic of the inside configuration with probability 1? So, so this is the kind of question we are going to look at. So, in other words, we are looking at spatial conditioning. So, we look at the conditional distribution of the inside points, which we denote by zeta inside a disk. So, our results hold more generally, but for the sake of discussion, we can take the case of a disk. And we are given the points outside the disk, which we denote by omega. And of course, in Poisson point process, this question is a triviality because the inside and the outside are independent. The points inside and the points outside are independent of each other. So first of all, in what generality do our results hold? So basically, we want bounded open sets whose boundary has 0 Lebesgue measure. So, but you know.
So one question, I mean the Geneva is a determinantal process, right?
Yes.
And the Gaussian zeros is also
No.
determinantal?
No. Right. So, the fact that Geneva is a determinantal process helps a little bit in the proofs, and the fact that the Gaussian zeros is not makes things more complicated. But for the sake of discussion, let us stick to the case of a disk. So, this conditional measure rho sub omega of zeta, a priori it lives on union of d to the n, where n is greater than or equal to 0. Basically, this is saying that there can be any number of points and anywhere inside the disk. But so what we are looking for is whether there are some further whether the reality is something much smaller than this. So, for example, for the Geneva ensemble, the points outside D determine exactly the number n of points inside D. So, the conditional measure, it actually lives on a much smaller set d to the n. And okay, so now we know that the conditional measure is rather singular, but how singular is it? So, we know that it lives on d to the n, but maybe it actually lives on a much smaller some positive codimension submanifold of d to the n. In other words, maybe the outside points impose some further rigid constraints on the set of inside points. So
when you say determine exactly, you mean it determines the distribution of the ends, right?
no, if you know the outside points, you can compute an integer.
Exactly the number of points.
Yes.
But how do you compute? Can you say how you can compute it?
Yes, I can give you kind of an algorithm. Yeah. So if you know the points outside, you can just turn this machine and get a number.
So you're saying even the points outside this number n is deterministic. It's not like
Yes.
and this is almost sure.
Yes. Okay, so now we want to know, now we have dropped down from union of d to the n to d to the capital N for some specific capital N which depends on outside. And we want to know whether this is all that we can say about the inside, or maybe we can say something more. So the answer turns out to be nothing more. So in what sense is it nothing more? Since there are capital N points, we already know. So we can think of it as a vector in d to the n, as a random vector, and we are looking at the distribution of this random vector. And in d to the n, there is a natural measure to compare another measure with. The natural measure is the Lebesgue product Lebesgue measure, and we show that the conditional measure is absolutely continuous with respect to Lebesgue measure. So there is no further singularity, and hence is a probability density function, of course. And this density is positive almost everywhere. In other words, these finitely many points inside the disk, they can be located in any arbitrary configuration, almost any arbitrary configuration.
So what's the density of your point process? Like your G-bar ensemble, so I'm trying to understand your scale. Your G-bar ensemble is in the disk of size 1 or?
No, it's infinite, full. Yes. Of course, for disk for a finite ensemble, this kind of question is a triviality, right? You know how many points are there in total, which is the dimension of the process. You know how many points there are outside, and you take the difference. I will come to that point in a moment, actually. So we have this conditional density, which is positive almost everywhere. And we can also show that this conditional density is actually comparable to the squared van der Monde density. So even under conditioning, the inside points, they show the same kind of quadratic repulsion in the space variable as the full ensemble. So any questions about this? Okay, so if not, so let me move on to the, okay, so let me say a bit more about the point which Professor Yao raised. So this is joint work with my supervisor, Yuval Perez. So,
I have one question.
yes.
These constants depend on the domain.
Yes.
And the other one.
Yes.
Are there special domains for which they coincide?
I don't think so. I would be very surprised if there is one. So
The G-bar ensemble is explicit on the atomic. So you condition on outside, then you can write down the Gibbs measure inside. So you say explicitly. And then you will get this van der Monde factors. So why is what's the main point of this result?
no, but it's an infinite ensemble, so you cannot really write it down explicitly.
So it's because you take angle infinity.
Okay, so we call a point process rigid if given the points outside a domain, we can predict the exact number of points inside. So precisely the same property which we have here. So of course, Ginevra ensemble is one, and another ensemble is any finite point process of fixed dimension, because you can just take differences of number of points. And a non-example is a Poisson point process, of course. One interesting question is that whether you can obtain the rigidity of an infinite ensemble like the Juniper ensemble by taking limit of, so the Juniper ensemble arises as a limit of finite ensembles. So maybe you can take limit of the rigidity, the natural rigidity in finite ensembles, and obtain the rigidity of the Juniper ensemble as a limiting behavior. So this is not the case because rigidity doesn't pass to the limits, and a simple example is this one. So you take n points in a disk of area n. So this is finite and rigid, and now if you take weak limits as n goes to infinity, the limit is Poisson because you chose uniformly, which is not rigid. So this is really something different compared to the finite rigidity of finite ensembles. So now we come to the case of zeros of random analytic functions. For Gaussian zeros, we can, so again we study this kind of question. We start with union of d to the n bigger than or equal to 0, and just like the Juniper ensemble, the points outside d determine precisely the number of points inside d. So from union of d to the n, we have dropped to d to the capital N for some fixed n. But in the GAF ensemble, we can say more. So the outside points also determine the sum of the points inside. So in other words, if there are n points, so this is a hyperplane, and you basically intersect your d to the n with this hyperplane. So again we have some submanifold on we have some fairly nice submanifold on which our inside points live, and the question is whether that is the entire truth or whether we can go down further or whether there are any other rigid constraints. So again on this submanifold we can define a natural Lebesgue measure with which we can compare the random vector of inside points, and we can show that the vector of inside points is absolutely continuous with respect to Lebesgue measure. In other words, we cannot say we can say nothing more deterministic about the inside points given the outside. So it has a density. The inside points have a density on this. So we are calling this sigma sub s. On this disk cut by a hyperplane, and this density is positive almost everywhere. So given the outside points, we know that there are so many points and they have such and such center of mass, so they live on the sigma s. But on this sigma s, they can be in any almost any configuration. And like the Juniper ensemble, we can prove estimate on the conditional density. So we can basically show that this conditional density is roughly proportional to the squared van der Pont density. So it has the similar quadratic repulsion in space variable. Any questions?
Question, I mean, so the Juniper is really the Coulomb gas of beta equal to 2.
Yes.
If you change beta, and you think you still have this deterministic property, or is it something which is special for beta equal to 2?
I think it will have the same property.
It should be independent of.
Yeah. Okay. So here is some proof sketch. Maybe I will return to it later. Okay. I mean, but I have some. I want to mention some applications. So hopefully I will have 5-10 minutes left in the end. Okay. So there are some applications which are which I want to mention. So the first one of them is to continuum percolation problems. So what is the model we are studying here? So maybe there. So what is the model we are studying here? So basically you have a point process on the plane, and you put a disk of a fixed radius r. Imagine that these are disks. And 2 points are connected if the disks intersect, so they are nearer to each other than a certain threshold. So this defines a connectivity structure on the points on the plane, and you want to know whether there are infinite clusters, and if there are infinite clusters, how many there are, etc. So usual percolation questions. So 2 points are neighbors if their disks intersect. And for Poisson point process, this is a well studied problem. It is known that there is a critical radius of these disks such that for radius smaller than the critical radius, there is no infinite cluster almost surely, and for radius which is bigger than infinite than the critical radius, almost surely there is an infinite cluster. And the infinite cluster, when it exists, is unique. So, so these results roughly parallel the results in bond percolation theory. So now we want to study this kind of this continuum percolation type of problems on these correlated point processes like the Ginevra ensemble or the Gaussian zeros. And but the proofs in the Poisson process use spatial independence in a very strong way. So for example, let me just sketch a part of the proof of the uniqueness of infinite cluster. So the uniqueness of infinite cluster, I mean it follows the famous Barton and King type argument. So suppose we want to rule out the event that there are 2 infinite clusters. So suppose this is the Poisson process, and these are the roughly the contours of the 2 infinite clusters, and what we do is that we intersect this with a big disk. So if R is big enough, the disk of radius R with center at the origin will intersect both the infinite clusters. Now what we do is that we fix the points outside, and we throw in a lot of points inside. So this can be done with positive probability since it's a Poisson process, and if there are a lot of points inside, the disks corresponding to these points will join up the 2 infinite clusters. So if you have 2 infinite clusters with positive probability, then you also have 1 infinite cluster with positive probability, which is a contradiction because the number of infinite clusters is almost surely a constant because of ergodicity. So this is the Barton and King type argument, but it uses spatial independence in a strong way. We can try to work around this, but still we want to be able to introduce a lot of points inside, and roughly this goes under the name of finite energy condition. So but as we saw in our processes like the Ginevra ensemble or the Gaussian zeros, there is no finite energy either because you are not allowed to introduce or remove points from the disk. So we in joint work with Manjunath Krishnapur and Yugal Perez, we show that for Gaussian zeros and Ginevra eigenvalues, we have similar results as the so we have a critical radius below which there is no percolation and above which there is percolation with probability 1, and the infinite cluster also exhibits uniqueness when it exists. So maybe so for example, if you want to so how do we use for example the uniqueness of infinite cluster, if you want to establish that for these ensembles, then we need to use the previous theorems which I mentioned on rigidity and tolerance. So for example, for the Ginevra ensemble, let me just quickly describe how we use our results. So for the Ginevra ensemble, we know that the number of points inside this disk has to be fixed, but they can be in any arbitrary location. Now the radius of the disk is, let us say, R. So roughly there are of the order R square points, and the distance which needs to be bridged is of the order R. So there are many more points than the distance to be bridged. So and these points can be in any arbitrary location. So what we can do is that we can basically we can move these points and without introducing any other points. We can move these points and join up the 2 infinite clusters. And this can be made rigorous, although there is some work involved in doing that. And a similar approach also works for the Gaussian zero process. properties as in?
Of the universality or anything like that about the transition. Let's just say in high dimension, we understand. I guess we understand percolation fairly well in high dimension. Do you understand a transition here in high dimension, for example?
No, these are all two-dimensional processes. These are all two.
No, but even in two dimension, you could ask, how this, how the size of the cluster and probability of being connected to the origin depends on R and
No, we did not.
I expect maybe a different universality class. Yeah, I don't know. That's what I guess I'm asking.
Yeah, I don't know whether anything is known about that. I don't think so. I don't think anything is known about that. Okay, so this is okay. So there are some other results. Maybe I will come back to them later. Okay, so maybe I have time. So we okay. So the next. So there are some other interesting corollaries on the way of deriving these results. So one of them is recovery of the Gaussian analytic function from its zeros. So if you are given a polynomial, if you are given the zeros of a polynomial, from there it is not possible. It is possible to recover the polynomial only up to a constant. If it is an entire function, then we can do some Weierstrass theorem type results, and then we can, in some sense, recover the entire function up to a multiplier, which is another entire function. But for the it turns out that that in the case of the Gaussian analytic function, so for this full entire function, if we know the zeros, then we can recover it up to a deterministic multiplier, which is random but is independent of the zeros. So in other words, if we are given the zeros, we can on the basis of the zeros we can construct an entire function which equals our original Gaussian entire function up to this factor gamma.
So you mentioned the result of Michel-Soden.
Yes.
Some uniqueness.
Yes.
So doesn't this just follow straight from that, or is there something else?
No, that doesn't follow. This doesn't follow straight. So that is basically saying that if you want a power series with Gaussian coefficients, and you want an invariant zero set, then there is a unique way to scale up to some multiplicative factor, and this is reconstruction. So these two are different things. This leading factor gamma, it doesn't depend on z. So in that sense, it is a constant. It's random, but it is independent of the zeros. And in some sense, this is the best you can do, because if fz is your Gaussian entire function, then gamma times fz, where gamma is a uniform random variable in S1 and is independent of the coefficients, has also the same distribution as f. So but they have the same zeros. So essentially, it is not possible to recover these gamma from the zeros.
Can you just put it equal to 1 or something, or why does it have to be random then?
No, I mean, the point is that you cannot tell this gamma from the zeros, because if fz is distributed as this Gaussian entire function, then gamma times fz also has the same distribution. Okay, and then there is some result on stability of inverse sums, but maybe we will skip that. So there are other applications to completeness of random exponential systems. There is a conjecture of Lyons type, which we can settle by this. You can use them to study mixtures of point processes, but I will but I will focus on the completeness of random exponential systems. So what is this problem? Okay, so suppose we are given a discrete point set on the real line. And then we can go, so for every real number we can consider an exponential function e sub lambda, which is basically e to the I lambda x. And for reasons that will become clear, we will consider this as an element of L2 minus pi pi. So given a discrete point set, we can consider the family of these functions corresponding to all the points in this point set. So these are the capital E lambda as it is written there, and we can consider we consider them as elements of L2 minus pi pi. So we can take the span of E lambda, and it is a subspace of L2 of minus pi pi. So the question is whether span of E lambda is equal to L2 of minus pi pi for some generic point set, and it is a classical question in harmonic analysis. It has been studied. There are long surveys by Redheffer and Levinson, Björling, Meliavin have studied this question, and the classical results are parameterized by some sort of asymptotic density of lambda. In this case, it is a Björling, Meliavin density. So basically, the classical results are of the, so these are results in the deterministic setting, and they are results in the following sense, of the following nature. So you have this asymptotic density, the Björling, Meliavin density, and if it is bigger than 1, then this is true. The span equals L2 of minus pi pi, and if this Björling, Meliavin density is smaller than 1, then the span is a strict subspace of L2 of minus pi pi. Now the question is what happens at density 1, and at density 1 it is a little bit of a tricky situation, because for example, if lambda is equal to z, this is complete, but if lambda is equal to z minus origin, this is no longer complete, right, because this is a Fourier basis. So but you can say that these are pathological point sets, maybe these are pathological examples. So I want a generic example. So what happens if we choose a generic point configuration, which is a point process? And as far as we know, the answer to this is not known, even when lambda is chosen from a Poisson point process of intensity 1. So so there is another a similar completeness question we can ask for determinantal point processes. So suppose you have a determinantal point process with kernel K and background measure mu, and suppose it is a projection onto a subspace H. So we know that for a determinantal process to exist, K has to be a non-negative contraction, but suppose its only eigenvalues are 0 and 1. So suppose it is an actual projection onto some subspace H. So then K is a reproducing kernel, and we can, given any point x, we can think of the following function E sub x. So given any realization of the determinantal point process, we can consider the collection of functions where the xi's belong to the DPP. So of course the span is a the span is a subspace of H, and we can ask whether this equals H. So it is known that the answer to this question is yes for any discrete determinantal point process, but nothing either way, yes or no, is known in the continuum setting. So for example, before our work, it was not known what is the answer for the Ginevra ensemble or for some other continuum determinantal point process. So we asked this question, and I proved that if in addition your determinantal point process is rigid in the sense that the points outside let us say a disk determine the number of points inside the disk in the sense of the Geneva ensemble, for example, then we have equality in this question. So, these random kernel functions indeed span H with probability 1. And how is this related to the question which I mentioned in the previous slide? So, basically you can apply this to the sine kernel process, and if you take Fourier transforms, then it shows that the answer to this question is yes, if lambda is chosen, if lambda is a random point configuration chosen from the sine kernel process on the line of intensity 1. Okay. So, any questions about this?
So, I guess I didn't understand the theorem. So, does it apply to the point process? Universe two-dimensional, one-dimensional?
No. The initial example is in one dimension.
Yeah.
This is in arbitrary space. So, and then you apply this to the sine kernel process in one dimension with intensity 1, and if you take Fourier transforms, you will get this L2 minus pi completeness.
So the sine process is also rigid?
Yes. And it also, so in the case of the 2 dimensions, for the you can ask a similar question to the sine kernel process. This time you can ask it with the Geneva ensemble, and your exponentials will be E sub z of w is equal to e to the z bar w, and you will, and completeness is considered in the Fogg-Bergman space, and this theorem shows that there is completeness in the Fogg-Bergman space for the Geneva ensemble. So, any questions about this? Okay. Okay. So, now let me talk a little bit about a hierarchy of point processes. So, we saw that the points, so we saw some examples where the points outside a disk or a domain, they determine the number of points inside. So, if there are n points inside, let us denote them by n. And if there are and if the sum is known, so the number of points we can think of it as the 0th moment of the inside points in some sense, and the sum we can think of it as the first moment of the inside points in some sense. So, the natural question is that to extend this idea is that is the following phenomenon. If you take a disk or some reasonable domain, the points outside this domain, they determine precisely the number of points, the first k moments of the points inside, and they do not determine anything more. So, on the constraint, under the constraints that these k moments are fixed, there is no, the points can mean any arbitrary configuration. So, Poisson is at level 0, so no moments are conserved. So, Geneva is at level 1 because only 0th moment is conserved. Gaussian zeros are at level 2, and the natural question is whether we can find some natural point processes for levels k greater than equal to 3. So, in recent work with Manju Krishnapur showed that there is a family of analytic functions with Gaussian coefficients such that the points outside the disk determine the first k moments and nothing more in this sense. So, basically they are obtained by taking psi k factorial to the alpha, and then it depends, and the degree of rigidity depends on this variable alpha. And no, alpha is fixed. K is the index of the power. I see. No. I mean, you can. I mean, basically, the level of rigidity changes at these points. 1 over 2, 1 over 3, 1 over 4.
But this process will not be ergodic, right? I mean,
No, 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 this is not an invariant process. And
And what you get here when k is, I guess, 0, does this correspond to?
well, for k equal to 0, well, k equal to 0, it is not an entire function.
Okay, so this is
I mean alpha 0, right?
Wow, you're mixing up the k's. So on the board, you're talking about k rigidity. You said that when
I see.
when k is 0, you have the Geneva is naturally k rigid, 0 rigid, 1 rigid.
1, 1.
Okay, 1 rigid. Does your example degenerate to the Geneva?
No, no, no.
Okay, so
No,
it gives
it's-
another example.
Yeah, it's a different family of examples. Okay, and another question we studied is the following. So suppose you have a determinantal point process, then in principle, if you know the kernel and the background measure, then you know everything about the determinantal point process. So it's the question is whether on the given the knowledge of the kernel and the background measure, we can say something about rigidity and tolerance. So there we have the following result. So we know that if you have a determinantal point process, then the kernel has to be a non-negative contraction in L2 mu, and we proved that if the kernel is a proper contraction, so in the sense that that it's not a projection. So there is some spectrum. It can have eigenvalues at 0 and 1, but it has some spectrum between 0 and 1. Then it must be insertion and deletion tolerant. So in other words, there cannot be any rigidity unless the kernel is a projection. Okay. Okay. So if there are no further questions, maybe I will.
Can you say that last thing again about? So what are the conditions for k rigidity for determinantal point process?
No, this is different from k rigidity.
Okay, so can you just repeat what
Okay,
you said?
so the result is the following. So if you for a determinantal point process, the kernel is the kernel defines a non-negative contraction. We showed that this a determinantal point process can be rigid only if the kernel is a projection.
only at 0 temperature it's rigid, and at finite temperature it's. You don't know if it's k rigid.
No. This is different from k rigid.
And it's not an if and only if. It's just
No, actually, if you for Euclidean spaces, we do not know the answer whether it is if and only if. But if you go to hyperbolic space, then you can construct a determinantal point process, which is a projection, but which is not rigid. So this this analytic function, it is like converges on the hyperbole on the unit disk, and the 0 set is a determinantal point process with respect to the hyperbolic measure. So and this is not rigid, so it is insertion and deletion tolerant. Okay, and how much time do I have? Up to 12. Okay, so maybe I will go back a few slides and discuss something about the proof. So I will mostly discuss the rigidity part, how to show that these point processes, if you know the outside point configuration, you can actually compute some statistics exactly of the inside points. So the simplest case is that of the number of points of the Gaussian analytic function. So we know the outside zeros of the Gaussian analytic function outside the disk, and we want the number of inside zeros. And the key tool is these linear statistics. So here nu is this random point configuration, so it's a random point measure. And we will in fact consider scaled linear statistics. So in pictures, Okay, so basically, if you start with a function like this, you are scaling and gradually making it very wide and somehow approximating the identity. So we consider the scaled linear statistics, and there is a result of Fourier and Sirelson which says that the variance of the scaled linear statistic goes to 0 as L goes to infinity at this rate. So here is how we are going to use or exploit this result. So we will choose a radial function phi. So basically, we can think of it in one dimension. And what we ideally want to do is to, so if your disk is here, ideally we want to compute the integral of the indicator against your point measure. But this is not good, because for all these results to hold true, phi has to be CC2 or regular like that. So we choose a test function phi which, for example, satisfies this. So and now we can compute integral phi d nu, and for any such function, it will be as long as it is greater than or equal to indicator of d, it will be the number of points inside d plus some function which is a function of the outside zeros. Okay, and given the outside zeros, we can compute this. So if we knew this, then we could compute this and we could recover this. Of course, we cannot do it for phi on the nose, but we can take scaled versions of phi and apply this for the scaled functions. And by this variance drop lemma, we have that the variance of integral phi d nu is very small. So we can roughly approximate it by the expectation. And the expectation, we can just compute it because we know the first intensity of the point process. And this squiggle sign, it becomes exact as L goes to infinity. So the error here vanishes, and at each stage we can compute this G sub L successively, and in the limit we can take the difference and obtain the number of points. Okay, so so by way of proof, this is for example what I wanted to say. So if there are other questions, I can go more into it.
So what about the Geneva ensemble case?
For Geneva ensemble, the problem is that we take a similar approach, but the problem is that this is not order 1 over L square, so it doesn't go to 0. It is of order 1. So there, we what we do is the following. So essentially, the idea is as follows. It is, so what we do is that we take several scales. So for any given n, we take phi of L1, phi of L2, phi of Ln. So you can think of, I think, taking Ln to be roughly of the order 2 to the n suffices. And then we take the aggregate. This is psi of n. And we do the same argument with psi of n d nu. And then it's a technical matter to show that basically the covariance between distinct Li and Lj, if for example they are chosen at this scale, goes to 0 as for example if Lj by Li goes to infinity. So they are decorrelated. And then the variance of this object will be roughly of the order n, some constant times n. And then you have, then since you are taking the aggregate, there is an actual variance drop.
But then outside this, outside the J ensemble, if you take any change the beta or do anything else, then where the proof breaks down. You cannot compute the correlation function precisely.
No, I think, I mean, we haven't written it down yet, but I think, for example, for the sine beta process, it will be true that they are rigid.
Sine beta is easier, but if you take the two-dimension J ensemble, but you change the Gaussian to something else, for example, or you change the beta of 2 to some other values, then can you get the same result?
Well, if it is, if you change it from Gaussian to something else, then I'm not sure actually. I mean, so this, for example, uses the correlation structure and everything. Yeah. But if beta is different, I would imagine that probably similar arguments.
You also don't have any of this fundamental formula.
But what is your intuition here? I mean, is it that if you have strong enough repulsion between your points, then that implies rigidity? Is that the intuition?
In some sense, in a very broad sense. But that is, so we have not been able to turn that intuition into a proof in any reasonable sense.
So that's what you believe is true?
Yes. Yes. So, for example, the Gaussian zero. So, as I mentioned in the beginning of the talk, these difference. So for example, the Gaussian zero process and the Gini principle, they have the same asymptotics of the whole probabilities, but they are. But really the Gaussian zero process is much more rigid in this sense, in that you have more conserved quantities. Yep.
I don't know if our talk is finished or not. We keep on asking questions. You have to say something more, please.
No, I think this is all that I wanted to say.
But the question is still welcome. Any question or comment? Yes, no voice. But what is question? All right. So thanks a lot. Thank you.
I lost my voice recently.
Yeah.
So I remember in the first few pages you mentioned rigidity including some cases.
Okay.
The random matrix models also have this rigidity property. Can you go back a little page?
You can come here.
More in this percolation structure.
And I think that I could be that it's not even
What can it go to home?
that it almost looks like a lattice.
For example, the eigenvalues of
Yeah,
for
for the finite case. For the infinite case, of course, I mean, this doesn't go to the limit.
okay, that's
Yeah, it could not be mine.
Okay.
Or it might be
Good.
You mentioned
Uh-huh.
K rigid.
Uh-huh.
Is it sufficient to calculate this type of linear statistics that are flat near the origin?
No, but basically you have to do that, but I think that's the kind of the only way. But
No, but I mean, is it sufficient? Or do you
yes,
have
I
to consider general linear statistics?
no, I think I mean, we haven't written that up as yet, but I think it's